One can still say more. As the development of modern set theory in the late 19th century and in the first half of the 20th century shows, a precise, elegant, systematic, and enormously fruitful theory of sizes for infinite sets can be built upon these notions of equal to, less to, and infinite to. Indeed, today, these terms are simply taken to determine the right notions of size. No need to attach indices to them in order to signal that alternative notions of size would also be available. It was one person who more or less single-handedly discovered this theory, the German mathematician Georg Cantor. However, it should be said that the definition of infinity is due to another German mathematician, Richard Dedekind. And both the theory and the definition of infinity are now part of what is called axiomatic set theory, which may be regarded as the foundation of all of modern mathematics, and which, by the way, we have all reasons to believe consistent. Now, here is something that I hope is bothering you. You might like the definition of infinity, and you might have begun to accept the concept of equal size on which it is based. But what's the big deal with the concept of has less members than that was defined before? For you might think to yourself, okay, the set 1, 2 has less members than 1, 2, 3. In turn, 1, 2, 3 has less members than the set of positive natural numbers, or the set of all natural numbers for that matter. And the set of positive natural numbers has equally many members as the set of even natural numbers, and so on. But that's just the following simple picture. Finite sets can be compared in size just as normal. All the infinite sets have more members than all the finite ones. And all the infinite sets are equal in size to each other. And so we could have just said that instead of bothering to analyze the concept has less members than in much detail. Well, wrong. As Georg Cantor showed by means of various mathematical theorems, the landscape of infinity is much more complex and fascinating than that. Most importantly, there are infinities of different sizes. Here is an example. Theorem. The set of natural numbers has less many members than the set of real numbers. Since both of these sets are infinite, this shows that there exist infinite sets x and y such that x has less members than y. By the set of real numbers, I mean here the set of all numbers that one can denote by decimal expansions in the usual manner, such as 0, which is equal to 0.000 and so on, 1, 1/2, which is 0.5000 and so on, 1/3 or minus 1/3, minus 18,233 plus 16 over 17, square root of 2, which is 1.4142 and so on, pi, and so on and so forth. Or alternatively, one can also think of the real numbers geometrically as the points on the real number line. Anyway, let me now try to convey the main idea behind the proof of Cantor's theorem. Note that I will suppress a couple of details that one needs to fill in if one wants to state the proof in completely precise terms. Issues to do, for example, with the fact that the real number 0.99999 and so on is actually identical to the real number 1.000 and so on, and the like. Think about that if you're interested, but I won't mind for now. Okay, by the definition of has less members then, we need to show the following in order to prove the theorem. First of all, the set of natural numbers has equally many members as a proper subset of the set of real numbers. Secondly, but the set of natural numbers does not have equally many members as the set of real numbers itself. The first part is obvious, since the set of natural numbers is itself a proper subset of the set of real numbers. So correlate 0 with 0.000 and so on, 1, 2, 3, and so on. We can simply pair off the natural numbers with themselves. So the tricky part is the second one. The way to prove it is what philosophers traditionally call a reductio ad absurdum, or what mathematicians often call an indirect proof. A method of proof that is actually related to Zeno's way of arguing. Let us assume for reductio that a set of natural numbers does have equally many members as the set of real numbers. From this assumption, we will derive a logical contradiction. Hence, the assumption cannot be true. So its negation must be true. That is, the set of natural numbers does not have equally many members as the set of real numbers. That is the logical structure of the proof. Now, let's carry this out. Assume for reductio that a set of natural numbers has equally many members as the set of real numbers. Therefore, by definition of has equally many members as, there must be a pairing off between natural numbers and real numbers. 0 is paired off with blah 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 point x01, x02, x03 and so on. 1 is paired off with blah 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 point x11, x12, x13 and so on. 2 is paired off with whatever point x21, x22, x23 and so on. Each natural number is paired off with precisely one real number and the other way around. By the meaning of pairing off, the pairing does not miss any natural number, nor does it miss any real number. By ... in the square brackets, I only mean that I will not actually care about the decimal expansion of our real numbers to the left of the point. Instead, I will only care about their decimal expansion to the right of it. By the way, on the slides, the point is colored in red. Now, when I say xmn, I mean the nth decimal place, that is the nth digit, to the right of the point of the real number that is paired off with natural number m. For instance, if 0 got, say, paired off above with 1/3, that is 0.33333 and so on, then x01 would be 3, x02 would be 3, x03 would be 3, and so on. Now we have to prove that assuming the existence of a pairing off between natural numbers and real numbers implies a contradiction. This can be seen as follows. One shows that a real number exists that is missing in the pairing that we had assumed to exist. But that's a contradiction, since by definition a pairing does not miss any members of either of the sets involved. Let me now describe a real number that must be missing in the pairing off above. I choose 0 to be its digit before the point. As the first digit after the point, take any digit that is distinct from x01. Since there are 10 available digits from 0 to 9, there is such a digit distinct from x01. Let that digit be y1. For instance, if x01 is the digit 5, then y1 could be 4 or 7 or the like, anything other than 5. Similarly, as the second digit after the point, use any digit that is distinct from x12, call it y2. As the third digit after the point, choose any digit that is distinct from x23, call it y3, and so on. In general terms, for all natural numbers n, let yn be any digit other than xn-1 n. The real number that we describe in this way is given by the decimal expansion 0.y1, y2, y3, and so on. This is certainly a real number, since it is denoted by a decimal expansion in the standard manner. However, its decimal expansion was chosen so that it denotes a real number that was missing from the pairing which we assumed to exist before. For 0, y1, y2, y3 differs from the real number paired with 0 at digit x01. 0, y1, y2, y3 differs from the real number paired with 1 at digit x12. The constructed number differs from the real number paired with 2 at digit x23, and so on and so forth. By altering the diagonal of the two-dimensional array of digits above, we have determined a real number that was not paired off with any natural number above, but by assumption each real number would have to be paired off with a natural number. That is a contradiction. So our assumption that a set of natural numbers has equally many members as the set of real numbers leads to a contradiction. Hence the negation of this assumption must be true. The set of natural numbers does not have equally many members as the set of real numbers. And that is what we meant to prove. But Cantor's methods of proof by diagonalization is really much more general than that. Cantor did not just show that the set of natural numbers is of smaller size than the set of real numbers. He also showed that the set of real numbers is of smaller size than yet another infinite set. And that infinite set is smaller than yet another infinite set, and so on. There are not just two infinite sizes, there are infinitely many of them. More than the size of the set of natural numbers, more than the size of the set of real numbers, and so on. And Cantor can do even more. He shows that one can measure the sizes of infinite sets in terms of new numbers, the so-called transfinite cardinal numbers. One can calculate with them in many ways, though not all that are familiar from the natural numbers, and so on and so forth. And all of this is part of modern set theory. We have not just found an answer to our question from the beginning of this lecture, what is infinity? We discovered a whole universe of infinities, Cantor's paradise, as the famous German mathematician David Hilbert once called it, from which no one shall expel us. It is a mathematical theory, set theory, that gave us the answer and which improved our understanding of infinity in unexpected ways.